hope we're all doing fabulously. I'd love to see if anyone is around and up for having a nice cheeky chat with me. Who is here so far? I've got some people saying hello and how are we? I hope we're doing really well. Just to let you know, my name is Josh. If you've not known me before, I am a science teacher at a usual school and in London, a normal school in London, in North London. It's a brilliant school. We're all going to be starting back in a week or two. I am really looking forward for this Thursday as well, because my year 11 students, who are about 15, 16, they're going to be receiving their GCSEs. I'm going to go in, I'm going to go say hello and see how they're doing. It's obviously quite high stress levels for a lot of people, so I'm looking forward to go in and hang out. But for now, I'd like to start up with some wonderful chemistry for this week. There is a slight change of plan for some of the timetables coming up, but as you can see, aujourd'hui, today, we have 11 AM high school chemistry. We're going to be doing some separating mixtures, forensic chemistry, which will be super fabulous. We've also got art school project with Dr. Jazz, which is just really cool. Firstly, as any names go, Dr. Jazz, wicked. On Wednesday, we've got biology, physics, English, physics, humanities. What? We're so lucky to have all these incredible things. Thursday, we've got physics. Then it should be me with chemistry. However, unfortunately, this has been cancelled and moved to 11 AM on the Friday. So if you're looking forward to some chem, then I'm going to be doing a little bit on Mendeleev's genius, who invented the periodic table. It is going to be so exciting. I'm looking forward to it. We've also got an inspiring guest coming up this week. How much stuff is on? It's incredible. By Dr. Sarah Pearson. And on Friday, you've got 10 AM some bio with Dr. Hannah Bolland. Me then at 11 AM for some chemistry, and then at 1 PM got music, understanding music with Dr. Jazz. Anyway, this is just so exciting. What I want to start with you all today, people that are on the chat, is this image here. I hope you can see it. This image, I wonder if anyone has seen before. This is an image of lots of ew, oh, it's not very nice. Oh, thanks for letting me know about Olivet 2008. That is totally fine. They can come whenever they like. But what are we looking at? And the question is, if you were a detective, yes, Mears 91 is gum under the desk, gum under a table, disgusting. I don't know if anyone's put their fingers under a table and felt it, and it's awful. But what I'd like to ask you all, the wonderful people of this chat, is, if you were a detective, right? If you were a detective, what methods might you use to work out who was the perpetrator, or who is the main perpetrator of performing this awful behaviour by putting gum under the desk? I want to see it in the chat. I've got my trusty Restream chat here. I'd love to see what you guys have to say. What might you do to try and work out who has been putting that gum under this desk in a school? You have a number of suspects. Arguably, the students that go to the class in that room where that table is. We've got this idea of security cameras. Lovely idea. Now, often security cameras are the only thing that's necessary. They're often very obvious. However, sometimes security cameras are not very clear. Furthermore, they're not always in every room. I mean, the room I'm in now doesn't have a security camera that I know of. I'm pretty sure it doesn't. I hope it doesn't. I guess the only camera is that one. I wonder if anyone's watching me. Anyway, what can we do? We've got the idea of DNA tests. Wicked. Now we're talking chemistry. DNA. I mean, what does that actually look like? We've got the idea of test the saliva, says Vendible Sugar. What are you testing it for, though? So there's definitely some sort of chemical test for the saliva, but how can we link that? That's interesting. See if the fingerprints oh, that is such a cool idea. We've got the idea of fingerprints. Hold on, where's my pen gone? It's over here. Fingerprints. Man, that is really cool. What else we got? Any other ideas? What else we got? We've got security cameras, DNA, saliva, testing their fingerprints. Anyone got ideas of really cool chemical ways that we could look at these? Some chemistry. Whoa, it's Piggy Lover 2010. Look who sits there and then ask if they have any gum, because if they say yes, say, can I have some? Just pass me the pack. Then they can't put any more on the desk. Keep doing it until they don't bring gum. What, so just continuously take their gum away from them. Interesting. So sort of like, it's kind of like a sting operation. I love that. In police work, they do a sting operation where they might set someone up and see if they have something on them. Cool. That's a really nice idea. Now, I wonder if anyone can tell me a test, some sort of test in chemistry. Now, you may not know the answer to this, that's okay, but there are a bunch of food tests in chemistry which students aged around 13 to 16 years old and a bit older. Oh, you are OMHNPH on a different account. Thanks for letting me know. Piggy Lover. I love pigs as well, to be fair. Pigs are absolutely adorable. Hashtag don't eat them, just love them. If you know about this, you may know about a food test which can be done, which can test the amount, the mass, not the exact mass, but just the general amount of sugar in certain substances. It's a very, very special test where you can test for sugar, right? This is a chemistry knowledge test. I wonder if you know what you need to add to. There's a special solution that you need to add to substances to work it out. Oh my gosh. We've got, firstly, Xenon994 saying hi, hello. We've got Piggy Lovers, hello, hello again. But Laura 4 has smashed it. The Benedict's test. Amazing work. You could take these gums and maybe do a Benedict's test on them, right? Do a Benedict's test which can tell you how much sugar is in it. And maybe you could then ask students who sit there for their gum and do the same test on their gum, and if it comes out with the same amount of result from the Benedict solution, then you'll have a lot more data on that. I love this. This is so cool. This is all part of today. Separating mixtures, forensic chemistry. Let's crack on. Now, to begin with, I'd like this straw poll to be, it's not, well, the thing is, as Xenon904 said, yes, it could be quite expensive, but oftentimes, when it comes to real crime, obviously, you know, this is not very pleasant, but you're not going to go to jail for it. If it was real crime, these kinds of tests that we're learning about today are maybe expensive, maybe they take time, but they can add to the evidence of building up a case to find the perpetrator. Very, very important. Now, if it's possible, I'd like this strawpoll.me to be posted so that we can go to it. I know that, for example, Mia's and some other lovely people and some other administratives might be able to help out. If not, that is okay. I wonder if we can type it in bit by bit. I wonder if I can just type it in like this. Let's see if I can do this. It would be straw poll. I'm going to add a space. .me /2 0 7 8 7 9 5 7. I wonder if that's going to work. Ooh, that kind of works. But just remove the space bar. Anyway, what I want to do is I want to learn about one of these 4 incredible separation techniques today. And what I'd like you to use the straw poll for is to tell me which one you'd like to do. But before we get into the straw poll, can you tell me what these separation techniques are based on the photos? We will say there's numero uno, numero dos, number 3, because I don't know the next number, and number 4. Uno, dos, 3, and 4. Mix up the language. I can do it in Japanese. Ich, ni, san, shi. Sugoi. Distillation is the 3rd. This one here is not distillation. Oh, the second one is not filtration either. Maybe Xenon904, you might have seen the different numbers, and it hasn't updated quite in time. What we think. Let's get some water. Hello, Talitha, 2006. That's a wicked name. Nom nom nom. Ah, you saw different numbers. Chromatography number 2, absolute legend. Yes, this is amazing stuff. Chromatography. Lovely, lovely. Chromatography is an amazing separation technique. Number 4 is distillation. Excellent work. Number 1 is crystallization. There's a wee crystal. Love it, love it. A wee crystal. You're completely right. We've got these copper sulfate crystals forming. This is crystallization. Excelente. We have crystallization. And the very, very final one. Oh, Alistone, 1 through 5. Crystallization, chromatography, filtration. Excelente. And distillation. Excellent work. Now, I'm going to click on this straw poll. I did post it in the chat. However, what I posted had a little space in it, so it was able to go through. I wonder if it would be able to work if I didn't put the space in. But what it is, hopefully you can see here, is the straw poll. And what I'd like you to look at is what separation technique do you want to cover most? Now, hopefully, let's have a go. I'm going to go to the results. I wonder if people have managed to get in. Ah! Some people have come through, which is fantastic. And what we're going to do with this straw poll is we're going to do it in order, from the most voted to the least voted, in that order of what we're going to look at and see how much time we've got. We've currently got about 35 minutes left. We'll see if we can get through all of it, but, you know, depending on timings, we're going to go from there. As we can see so far, we are currently 2 votes on chromatography. If you can get onto the website, let's see if I can do that again. I wonder if I can I just copy and paste? Can I copy and paste? Now, unfortunately, when you try to post a message, Mears has put it forward, but what Mears has got is a little space in between the last letter of straw poll and the first dot before me. So if you want to type that in without the dot, then it'll work. Unfortunately, it might not work. Let's see if I can do it. Straw poll dot me /20787957. 207. Is that going to work? Oh, it's worked for me. Hold on, has it come through? Let's have a look. Let's have a look. That's fine. Ah, it has worked. Ah, oh, because I'm logged in on my phone. Fabulous. Hello, it's me. 3 or 4 times. Right, let's have a look. Right, click on that. We have currently got 5 votes in. No one's in for filtration. But we've got 1 for crystallization, 1 for distillation, 3 for chromatography, which I'm really excited about, 4 for chromatography, 5 for chromatography, 2 for crystallization, 1 for distillation. Oh, it's neck and neck with crystallization, distillation. Distillization? Mate, I'm just too excited. I can barely speak. We've got 3 for crystallization. Look, I think I'm going to come back to this. It's quite obvious that chromatography is winning. I'm going to come back to this and see what's up. We're going to start with the magic that is chromatography. I hope we're excited. I'm going to skip a bunch. Here we go. Whoop, 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 whoop. Chromatography. This is chromatography. Yes, the most exciting race of 2020. This is chromatography. I'm actually going to just do a quick thing. Ooh, what's going on here? Chromatography, I'm going to get you to come up later because I want to just focus on this. Oh, chromatography is... And I'm going to throw some words out. Beautiful. Oh, lovely. Would anyone else like to add some words just to this? I think it's cool. I'm so excited that this was the first one because actually it is my favourite. It's beautiful. Is there going to add any other lovely adjectives based on this? I think it's beautiful. I'm going to go for pretty. Oh, it's so pretty. Anyone else got cool ideas of what this is? Very colourful. Oh, I love that. Very colourful. A work of art. Colourful, yet soggy. I like that. Bit soggy. Yes, very, very nice. Anyone else got any cool words for it? Man, I love chromatography. It's so cool. Alright, so I'm gonna go away from the English language. Whilst it is a most wonderful English language, I think we should crack on with the wonderful science. Masterpiece! Fabulous. Yes, masterpiece. This is gorgeous. Now, what's stunning, really nice, what we're looking at is an incredibly important technique in separating a certain type of liquid, okay? So if anyone is writing notes during this, which I'd suggest if you were doing any form of exams in this, if not, you're welcome just to enjoy. If you're writing notes, this is an important aspect. It separates something called miscible liquids, right? Miscible liquids. Now, the word miscible means is able to mix, can mix, right? So, for example, water and oil are immiscible. They do not mix. But in this case, we have ink, right? A lot of the time, chromatography is used with ink, especially this kind of chromatography, and miscible means it can mix. In ink, usually ink, right? Because inks can mix together. Now, what we can see here on the right is here we have 3 inks and they're starting to separate. Now, the wonderment of this is that you'll see that all 3 of them start as a kind of brown, as a kind of purple, and as a sort of black colour. But as they separate, you actually see that in all of them, they all share a blue. And that to me is just fantastically interesting of chromatography. Chromatography, in its process, will separate an ink out based on a number of different factors. That the main factor that it will separate it out on is how likely it is to dissolve in water. So in this case, the blues, because they're at the top, they dissolve really well in water, and the lower colours, this kind of browny yellow, this purple, and the kind of different colours within the black, they clearly don't dissolve as well in water because they don't go as high. So the more dissolved, the higher it goes. And what we can see, because it's all at the same level, is that all 3 of them contain the same blue ink. And that's just so interesting. Let's look at chromatography in a bit more detail, but this time from a slower perspective so we can see. Now, this process of how to perform chromatography is basically part of the learning that around about 14 to 18-year-olds will need to know. And it's based on a number of different things, okay? What we start off with is our ink spot, right? This aspect here is our ink spot. And then what we do is we will put that on a line across here, right? Now, this red line I've put there, I'm actually going to delete and put in a different colour. I've dropped my pen. I'm going to put in a different colour. This time I'm going to put it into the colour, let's say black, because that's going to represent my pencil line. So we put our ink onto our pencil line. Can anyone tell me why, this is not the neatest, why would we put it on a pencil line? A pencil line, rather than like a line drawn in ink, for example. Why do we do it in a pencil line? This is quite important. And it's something that may be asked about in the examinations. And you've got an idea why we put a pencil line. Put a pencil line across, keep it even, then we add our ink spot. Amazing work. Mears 91, Vendible Sugar, Piggy Lover. It doesn't dissolve in water, which inks will do. Good, it could model results if we did it in a different colour. Good, so we've got our pencil line. We then put our ink spot on it onto this very special paper. This is chromatography paper. Now, chromatography paper is quite special because chromatography paper has many teeny tiny holes in it, kind of like a sponge. You know when you get a dry sponge and you put it like next to a puddle of water. So I'm going to draw this very quickly. Let's say you've got a little sponge like so. Here's my lovely cuboid sponge with all the little holes in it. Let's say you put it right at the edge of a puddle of water. Because it's a dry sponge, it's actually going to absorb that water. That water is going to go into it. It's going to suck in that water and take it in. This special chromatography paper is similar in that it has many holes in it to allow it to absorb water or absorb liquids, it doesn't have to be water, right, through a process called capillary action. So the chromatography paper is special. It is able to absorb liquids because of its many holes through a process of capillary action. So special chromatography paper. Really, really cool stuff. This is why I love chromatography. There's such brilliance in it. I'm going to just keep the word capillary action there. So we've got a special paper, and we attach it to a piece of wood just so it's at the top. Then we dip it into something like water. It can be water, it could be something else. I'm coming back to that in a second. So, for example, it could be ethanol. The reason for that we'll get onto in a second. That water then slowly, by capillary action, goes up the paper. Now I've drawn these lines as squiggles. It's not going to like snake up the line, up the paper. It will just go directly upwards, but this squiggle is just to show movement. And it will go up the special chromatography paper, and it will then go past the ink spot. And this is where the magic happens. It is so cool. So what you can see afterwards is the water has risen up, right? The water has risen up. In doing so, the soluble, which means the items in the ink, is able to dissolve, right? The items in the ink that are able to dissolve will dissolve in the water and start to be carried by it. However, as you can see, there is now a difference. There's this separation. This initial black ink spot has been separated into 1, 2, 3, 4, 5, 6 different colours to make up that colour black, which is just fascinating. Now over to you, the wonderful people. What of these colours is the most soluble in water and the least soluble in water? Over to you. I'm really sorry to Piggy Lover and anyone else that is afraid by my exuberant exclamations. I get very excited, especially when it comes to chromatography. But can you please tell me which of these colours is the most soluble and which is the least soluble? Vendible sugar is right in. I'm going to change my colour to my trusty light blue. We have yellow as the most soluble. Excellent work. Most soluble. What that means is it's able to dissolve in water the most easily, therefore will be carried up the highest. Every single ink colour will differ in how soluble it is. I'm thinking it's either yellow or purple, either end of the spectrum. Lovely idea, Mears. Yellow is the most soluble. The farthest travelling is the most soluble. Incredible work. Piggy Lover. Yellow is most. Purple or grey is the least. Excellent work. So as you can see, this we have the least soluble. Right. I mean, you've done it. That is the basics of chromatography. I'm going to add 2 more terms. For anyone here who is doing exams, you may, in your specifications, need to know about the following terms, okay? The following terms are the stationary phase and the mobile phase, okay? So this is the stationary phase, because it stays still, right? The stationary phase, which in this case is the paper, right? The stationary phase we would label as the paper. And in this case, the water is the mobile phase, because it is what is moving. Lower colours are most attracted to the stationary phase. Holy monkeys! Aliston135 has jumped every gun that I've come up with and absolutely smashed it. The lower colours are most attracted to the stationary phase rather than the mobile phase. Incredible work. So in this case, the purple and grey is attracted to the stationary phase, which is the paper. So they're like, nah, I'm going to stay here with the paper that I'm already attached to. I don't want to go with you, mobile phase. And the yellow is most attracted to the mobile phase. and therefore we'll be like, you know what, screw you, paper, I'm going to go with water, because water's my friend, and that's my mobile phrase, and sort of go up with it. Now, incredibly stated by Alison135, if you want to write notes, that's the person to be following. Now, my final question, before we get on to the real live applications of chromatography, my final question for you all is, why might we use ethanol rather than water? Sometimes we'll literally have to use ethanol rather than water. Why might we need to use ethanol rather than water for this experiment? Anyone got any ideas? So we've got this ink spot. Because something might not be soluble in water, Mears, you are a genius. Tell me, Mears, this ink spot, if it's not soluble in water, can you give me an example from the world of an ink that is not soluble in water? Give me an example of an ink that is not soluble in water. Brilliant, Alison135. It is a better solvent. Excellent word. Hold on, let's write that down. A solvent is a liquid, things or substances dissolve into. Excellent. So oil paints, incredible work, Mears. That's a great example of something that may not dissolve in water, because oil, by definition, will be it's called hydrophobic. It's hydro means water, phobic, like afraid of. It doesn't want to be in water. There's a very common pen I'm thinking of that is very, very resistant to water. And it's the kind of thing that if, for example, you had like a crime note written, and it was written in this pen, water would not be good to make in order to separate that ink out. Anyone got an idea of a special type of pen where it is specially made to be resistant to water and other smudginess? Anyone got an idea? A Sharpie! Mears91 on fire! We have a Sharpie. A Sharpie is a brilliant example. If you were, exactly, permanent marker, incredible work. Yes, everyone. Oh, you guys are smashing this. If you were to, for example, write on a whiteboard in usual whiteboard pen, then usually get some water, wipe it straight off, or just wipe it straight off normally with a board rubber. But if you were to use permanent marker, for example, a Sharpie, which is just a brand of permanent marker, a normal board rubber wouldn't work, and you're going to have to trust me with this. If you pour water on it and give it a wipe, it's still not really going to work. If you add ethanol or an alcohol-based solvent, like board cleaner, that's got ethanol in it, it will remove it. And that's why you might use ethanol instead. However, if you use ethanol, if you use ethanol, it will have very slightly different results in this. This result, this is the results you'd get, is called a I'm going to write it below actually because I've not given myself enough space. It is called a chromatogram, a chromatogram. Now, check this out. I did some research into a man called Theodore John Kaczynski. Theodore John Kaczynski is someone who is also known as the Unabomber. Right? Now, Theodore John Kaczynski was someone who unfortunately committed a number of crimes over a number of years by posting bombs in the post. Right? He posted bombs to different universities and airports and other places via the post. He is currently in jail. They've caught him. He's currently in jail. Now, I don't know if you can quite read this letter that he has written, but he's written a letter to journalists to say that someone is writing letters that isn't him, saying that he will do interviews. Now, Theodore John Kaczynski often will never do interviews. He's someone who doesn't really want to ever do interviews. So he's writing here look, I'm writing to say that this is a fake letter that you've been receiving. I don't want to do interviews. And it got me thinking that chromatography could be used to work out if the letters that these journalists are receiving are actually from Theodore John Kaczynski or from someone else. And here's why. In prison, because unfortunately the straight, hard pens can be used as a weapon or to hurt someone, they've brought in special pens like the ones on the left here that bend, so you can't really hurt someone with it. If you were to poke them, it would just bend and not cause any damage. And it's very likely that Theodore John Kaczynski was using this special type of pen only, because that's the only types of pen that people in prisons are able to use. Therefore, if you were to use chromatography on the ink here that Ted Kaczynski has written, it should be exactly the same chromatogram results as the ink used in these special prison pens. And if you were to use chromatography on these fake letters, then they should have a different chromatogram. What I mean by that is, if I were to give you an example of two chromatograms that were different, let's say, here's my chromatogram, and here's the ink that they started with, right? Then the real letters might have results that look a bit like this, but the fake one might have results that look a bit like this, whereby the one on the left you can see has 4 different types of ink in it, but the one on the right only has 3 different types of ink in it. You can tell that as a difference. I'm just going to mic drop for a second because this is so cool. Like, this is, I just find this this is incredible. And you can do this at home. All you need is like a bit of filter paper, and you can do this. Oh, it's so beautiful. Anyway, I'm going to stop there for chromatography. We've got about 15 minutes to half an hour left. I'm going to go back to these here and just check out the straw poll, see if anything's changed. It seems that people would like to look at crystallization. Now, Mears91 has asked, have they done this on the letters? And the answer is actually no, because they didn't really feel like they needed to. But if they did, they would get these kinds of results, which is really cool. Oh, mate, I am thirsty. We're next going to go into crystallization, which is beautiful. Oh my god, I was so excited to find this GIF. Oh, it was so excited to find this GIF. It took me ages to find a GIF like this. But this is crystallization in nature. It's beautiful. It's beautiful. Please, what are we looking at? You tell me. I'm going to stay quiet. This is a time lapse. So it's over a long period of time. Please tell me what we're looking at. I think it's just such a gorgeous, I feel like I can see the heavens in there. I can see my future. It's lovely, it's positive, everything is, right, a dewdrop drying. A dewdrop drying. Wow, say that 100 times really quickly. A dewdrop drying, really, yes. Water dissolving. Lovely idea of the word dissolving. But in this case, it's not dissolving. Can you think of another word other than dissolving? Dissolving is when a substance will go into a solvent like water or ethanol. And for example, if you put sugar in water, it will dissolve and the sugar will seem to disappear. But actually, it's being broken apart by the molecules of water. Alistone 135, water evaporating from a leaf. Brilliant work. Laura 4 is evaporating water drop, leaving behind other substances. Oh, this is why I love this GIF. Well done, Laura and Alistone. Really, really nice job. I love that everyone else has given some nice ideas from Xenon and Piggy Lover. But we've got this idea. We've got evaporation. Evaporation, which is when a liquid, looks like a G to me, a liquid becomes a gas. And what you've got here is this water slowly evaporating to become a gas. So the water is moving away to become, it's separating basically, to become water molecules in the air. And as Laura said, it's leaving behind this kind of film. Can you see that little, right there, that little film of substance? It's leaving behind a sort of substance. That substance that it's leaving behind are crystals. Because essentially crystallization is when a liquid... Quick, slurp it up before there's no water left. I mean, look, at a hungry, lovely little animal might want to slurp it up before there's none left. The magic of crystallization is, it's as simple as you get a liquid. In that liquid is a dissolved substance. Maybe sugar, maybe salt, maybe a poison. We'll look at that in a second. That water or liquid evaporates. You get that water to evaporate, and what you've got left behind are crystals, and those crystals, that crystalline structure, is different. Now let's have a look. Yes, Alison Montefiore, you can just at the bottom right here see another resultant from a droplet. Now I'm going to get rid of this GIF, unfortunately, because it is beautiful. I could watch it for days, but let's have a look. This is in a laboratory what you might do. Okay, what we have here is a Bunsen burner warming up just some general water, right? This water here. Now that water is starting to boil, and then that water is heating up this solution, right? Is warming up this solution. Now a solution is what occurs when you have a solvent, such as water or ethanol, and a solute dissolved into it. Examples of solutes are salt, sugar, or what we're looking up later, cyanide, which is a deadly, deadly poison. So we've got this is copper sulfate solution. So what they've got is this substance called copper sulfate that's dissolved in water. Okay, they've got this copper sulfate and it's dissolved in water, and they're like, actually, I don't want it dissolved in water. I just want the pure copper sulfate crystals. And this is what happens. As this boiling water is heated up by the Bunsen burner, it then transfers heat a bit less aggressively than a pure Bunsen burner, basically. You're using the Bunsen burner to heat up the water, and then the water kind of just gently heats up the solution above. You don't want to overheat it, otherwise it could boil and become dangerous and spit and spat at you. And that's why we wear goggles, by the way. So we use boiling water. And slowly but surely, the water in the copper sulfate will start to evaporate and go into the atmosphere. And what you're left with over time, T-I-M-E, time, is a lovely, beautiful copper sulfate crystals. Now, what I didn't do, which I really should have done, is show you pictures of copper sulfate, because copper sulfate crystals are so beautiful. Look at all of this! Isn't it gorgeous? There are some really, 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 really cool things you can build. I mean, look at this. This is a video on how to make massive crystals. Gorgeous. Copper sulfate crystals are really, really pretty. Oh, what have I done? Really, really, really pretty. And it's the kind of thing that we can do in school sometime. So, this is the basics. Oh, golly. Crystallization is where you have a solution whereby you've got a liquid solvent which has a solute, such as salt, such as water, such as salt, such as sugar, such as copper sulfate, or such as a cyanide, a deadly, deadly poison. And you have it in the liquid. Sometimes it can be indistinguishable. Sometimes you can't even see. Luckily, copper sulfate solution is very gorgeous blue. But in some liquids like this water here, there is going to be some dissolved things inside this. There's going to be dissolved chlorine in this, for example, because it needs to clean it, or is it fluorine? One of the two, to clean out my water. I got this from the tap. There are also going to be some other dissolved bits and bobs in here. That's actually what gives it its taste. Fun fact, if you drank pure water, 100% H2O, it's actually really bad for you, because water likes things to be dissolved into it. So as you drink the pure water through your digestive system, it's going to sort of take away solutes from your body into it, and then you'll urinate it out, and you'll actually end up with less solutes in your body, things that you need. So, this whole process is based on the idea that the solvent has a lower BP, or boiling point, than the solute. Okay? So, did you know that water boils at 100 degrees? I know, 100 degrees C. Crazy town. But did you know that salt boils? Actually, I'm going to leave it there. What do you guys think? What temperature does salt boil at? I'm really interested to see what people say. What temperature does salt boil at? What do we think? Got some ideas coming through. What temperature is about 1,000? Nice idea. Any other ideas? Any other takes? 2,000. Dunno. It's definitely going to be higher. Definitely going to be higher, because if it was lower, if it boiled at a lower boiling point, then the salt would leave the substance before the water. The answer is 1,413 degrees C. 1,413 salt will boil at or evaporate at. 1,413, which is obviously so much higher, right? So what that means is the boiling water will heat up the liquid above. That liquid above with salt and the water will evaporate because it's high enough temperature, but the salt will stay behind. Really, really cool. Let's check this out in real life. Now, if this ever occurs, where you become a detective in a forensic case, and you find that someone has unfortunately died, but near them is, for example, a glass of wine, a glass of water, a glass of some form of liquid, then you can use crystallization and some of the other things that we've done today to work out if there's any dissolved solutes in it that maybe shouldn't be. Now, cyanide, or potassium cyanide, which has the chemical formula KCN, potassium, carbon, and nitrogen. Potassium cyanide, a small drop of it can cause immense damage to the point of death. And a kind of fun / terrifying fact, why here is there a poison symbol on an apple? Why is there a poison symbol on an apple, and what does it have to do with this? What do we think? What do we think? Apple seeds, Alastone 135, Xenon 994, apple seeds contain cyanide. Apple seeds contain cyanide, right? Now, this is, because we've got so little time left, I'm going to have to finish here, but fun fact, this is my fun fact of the final part of the lesson. When, years ago, many years ago, people who were in positions of power were often, well, not often, if they were ever attempted to be assassinated, sometimes people would try to poison them, poison their wine specifically, with potassium cyanide. It's so deadly that you would drink some, you'd be conked out. You only need a few drops. So what people in power used to do is they used to eat apple seeds on purpose. Every day they would have a certain number of apple seeds, and what that would do is, they believed, build a resistance to cyanide. And I just think that's really, really cool, just as a concept. But the idea, to finish with this, is that if there is a substance that you have, for example, I highly suggest doing this with, for example, like a sugary drink, to work out how much sugar is in that drink. You get the sugary drink, boil it for a certain amount of time, the water will evaporate from the sugary drink and you'll be left over with this sugar. You'll see just how much sugar is left inside. A really cool idea. That is crystallization. That was chromatography. On Friday this week, 11 a.m, we're going to be looking at the periodic table, Mendeleev's genius. It's been an absolute pleasure to talk to you all. Thank you so much. If anyone has missed out and really feels like they wanted to learn about distillation, which it seems a number of students did want to do, there are some fantabulous videos on the YouTube where you can look it up. If you look up just distillation, science or something like that. There's some really, really cool videos out there for you. It's been an absolute pleasure. Lovely to see everyone. I hope you have a really nice rest of your days. And if you are going back to school soon, looking forward to getting you learning in the classroom once again. Have a great time. See you later.